오케이. 네, 안녕하십니까. 저는 콴델라 코리아 업무를 담당하는 안도현이고요. 공지가 나왔겠지만 이번 주는 아카데믹 세션을 저희 콴델라에서 진행하게 되고 그 일정이 조금 변경이 생겨서요. 금요일 일정은 없고 그 두 번째 아카데믹 세션도 금요일 일정은 진행이 되지 않을 예정입니다. 그래서 오늘, 내일 양일간 2시간씩, 1시간씩, 1시간씩 이제 강사분들이 변경이 되면서 강의 진행을 시작할 거고요. 네, 그러면은 이제 저희 그 콴델라에서 그 어플리케이션 쪽 담당하시는 아르노와 저희 CPO이신 장제너럴트님께서 강의를 시작해 주시겠습니다. 네, 감사합니다. Yeah, Arno, if you can share your slide and you can start.
Perfect. Thanks a lot, Nunyong. So, can you see the slides?
Yes, I can see your slide.
Perfect. So, Jean will start the beginning of the presentation, then I will take over. So, I leave the floor to Jean now.
Hello, everybody. So we will introduce this first class of program Mastering Quantum Computing with Photons. So first, to present ourselves. I'm Jean Senellartga, so I'm Chief Product Officer at Quandela. I've been working for 20 years as a AI expert in Sistran, which is a natural language processing company. I've been creating an open source framework, OpenNMT. And I've been working for Quandela for 2 years now, and where I launched a framework that's called Perceval, which it will be used in this class to program and simulate photonic quantum computer.
On my side, so my name is Arno Ricouwa. I'm leading the quantum application team at Quandela. So we basically developing cutting-edge algorithm using Quandela's hardware. And so I joined Quandela 2 years ago as well. And well, maybe the main project we're working on with the application team now is the delivery of the quantum toolbox, which is like a high-level set of primitives that are meant for people not especially expert in quantum computing to use our device and some of the algorithm you can run on.
So first, a quick word on Quandela. So Quandela is a French company. It has been founded in 2017. Today, we are more than 50 PhDs and engineers working in different fields like algorithmic, semiconductor, optical technology, computer science. And we have four offices, a research center, a factory where we are producing quantum computer, a clean room where we are building and making semiconductors that we are using for computers, and a research institute also. We are based around close to Paris, but we have also an office in Munich, Barcelona, and in South Korea. Just about what we are, our presence on the quantum field. We have today QPU online for more than 1 year, which is a 6-photon computer that is freely available on cloud.quandela.com. And this QPU has been available more than 90% of the time since the last year, so very high availability. And this has been published in different papers, and we'll give you reference to that during this class. Just a quick word. So we have launched our factory a few months ago, and we have delivered our first on-premise quantum computer 1 month ago. On the left picture, there is the founders of the company. there is the French Ministry of IT, and there is Alain Aspect, who is the 2022 Nobel Prize, who is a scientific advisor of the company. So this class is composed of 4 weeks of training, and our goal is to introduce the photonic quantum computer and photonic quantum computing. So photonic quantum computing is different from gate-based quantum computing that you may already know, and covers a lot of different topics. So in the first week, we'll be describing what it means to compute with photons, the basics. We'll talk about the mathematics of the computing with photons. And we will give you an overview on a photonic quantum computer in tomorrow's presentation by Nicolas Marin, who is leading the hardware production. The second session will focus on photonic algorithm. So there is quantum algorithm, but there is also dedicated photonic algorithm. We'll talk about the physics of quantum dots. Quantum dots are what we use to generate single photons that are used in our quantum computer. And we will give you some overview on the benchmarking, how we can benchmark a photonic quantum computer and compare it with a gate-based quantum computer, for instance, the one from IonQ, from IBM. And we have made a lot of benchmarks. And the weeks 3 and 4 will be a hands-on class. So with Perceval, the framework to program and simulate photonic quantum computer. We will give you access to a QPU online. That's where we will be able to make some exercise, and we'll give you access to a very powerful simulators that can simulate up to 25 photons based on GPU. So this week, what the topic that we'll cover are very broad, so with a lot of different topics. So I hope that we'll be able to follow. If during the presentation you have any question, please feel free to use the chat of Zoom, and I will be trying to answer the question as they go. So this the first class will be 1 hour led by Arno. We'll be presenting you these following topics. Then in 1 hour, there will be Shane Mansfield, who is a quantum computer scientist that will present you the mathematics of quantum computing. And then we'll take over tomorrow at the same time. So we are very glad to be there and to share with you our passion about photonics and photonic quantum computer. And again, feel free to ask any question. There is no bad question. We'll be answering the question. And we hope that you will be enjoying the class as we are doing it today. So it's up to you, Arno.
Thanks a lot, Jean. And without further introduction, let's move on to the goals of this session. So I will first provide you a historical perspective of what happened with light and then with quantum computing. And you'll see that quite interestingly, like the history of light and the discovery of quanta of light by Albert Einstein and Max Planck will lead us to like quantum mechanics and further down the road to quantum computing. Then we'll remind or make you discover the basic properties used in quantum computation and give an overview like the must-know quantum algorithm that provide the speed-ups. So the history of light started with Euclid in 300 before Christ. He was the first one in his book Optica to talk about the fact that light is traveling in straight lines, and he also was the first one to give a mathematical description and study reflection of light. Fast forward to René Descartes in 1630, where that's the beginning of a modern physical optics. So René Descartes assumed that light travels faster in dense medium, and he was the first to make an analogy between light and sound waves. A bit later, Sir Isaac Newton described light as with a particle theory. He believed that light was made of like particle because they could not travel in a straight line. And well, this explanation was against the wave nature of light. So we start to see that there is like contradiction between scientific in the like nature of light. Is it a wave or is it a particle? Then Léon Foucault and James Maxwell in 1850 and 1862 gives further arguments toward the description of light as a wave theory. So they were the first to accurately measure the speed of light. The wave theory of light become popular, and the community abandoned like the particle theory. And they study, of course, the famous Maxwell equation, so the electromagnetic radiation and their connection to light, and discovered that the electromagnetic waves, they travel at the speed of light, and derive the light as a form of electromagnetic radiation. And then a really crucial discovery for the history of light is the first milestone towards quantum theory was the discovery of Max Planck in 1900s, where he suggests that light, despite light being a wave, it can also lose or gain energy only in finite amounts. And that's the first time we introduced the notion of quanta of light to describe these discretized amounts. And this was again used by Albert Einstein in 1905, and he suggested that the light energy is carried in discretized quantum packets. For that, he received for this discovery, he received the Nobel Prize. And later on, in 1926, Gilbert Lewis named these light quantum particles photons. And in the same way, Planck and Einstein discretized the way light was exchanging its energy. Bohr did it with atom, where he showed that there was a limited number of orbits that were allowed for an atom. So the orbits of the atom were quantized as well. And this leads us to 1927, sorry, and with the famous Solvay conference where we had Max Planck, Erwin Schrödinger, Werner Heisenberg, Niels Bohr, and Albert Einstein. And the topic of this Solvay conference was to formulate a quantum theory. So with the subject of electrons and photons. And it turns out that they gave a first description of quantum theory through quantum mechanics, and they were pretty happy about this one, as quoted by Werner Heisenberg. So here's a quick recap of what we just saw. So for a brief history of light, which started in 300 before Christ with Euclid, with the first scientific description and interaction with light. Moving on to René Descartes, with who described light as a wave. Then to Newton with his particle theory of light, and Foucault measured the speed of light. Maxwell, who described light as a form of electromagnetic radiation, and then Max Planck, who said that the light energy is composed from finite elements, which were then called further used and demonstrated by Albert Einstein in 1905. and later called Photon in 1927. And this, after Niels Bohr having a similar description of its model of an atom with discretized molecular orbitals, led us to the formulation of quantum theory during the Solvay conference in 1927. But now what's with the history of quantum computation? So I will give you a first start with like a definition of what a quantum computer is, like more informal definition. And then we talk about the different properties used in the quantum computers. And then we mention the different types of hardware and move on to the main quantum algorithm and speedups. I mean, let's say like the seminal one, the one like students should study throughout this curriculum in quantum computing. So as coined by Ashley Montanaro, a quantum computer is a machine designed to use the principle of quantum mechanics to do things which are fundamentally impossible for any computer which only uses classical physics. In a sense, a quantum computer is the ability to extend the Moore's law, since we, like people in this supercomputing industry, realize that they now reach a ceiling, like the chip becomes so tiny that one needs to take into account quantum effects if you still want to double the power of machines every year. And you can see on the right a picture of a Quandela, which is one model of Quandela's quantum computer. But the first one to introduce the idea and this notion of quantum computers was Richard Feynman. I'm sure even if you haven't studied quantum computation, you may have seen this super famous quote by Richard Feynman in 1982. And where he claimed that no device can simulate quantum mechanics efficiently, but a quantum computer would be able to do so. And 3 years later, in 1985, David Deutsch gave a mathematical formulation and like a computer science formulation of a quantum Turing machine. And this was like the first time a quantum Turing machine was mathematically introduced with a theoretical formulation of it. But so now that we see some definition, informal definition of quantum computers, what a quantum computer is made of and how does it work? So first of all, you need qubits, which are quantum bits, so the elementary the like fundamental elements of a quantum computer. As you can see on the left, like a bit is discrete, can be either 0 or 1, whereas a quantum bit is represented not like 2 points, but in a sphere that we call the Bloch sphere. So it's a 3D sphere which represent all the state of 1 qubit. Then one needs and exploits superposition in quantum algorithm. So what is superposition? Let's say that you have some basic states. It could be emotional states, for example, like you're happy, you're in love, you're sad. Then you can be like in a superposition of both. Like you can be either happy and in love, or sad and happy. It can happen, even though it sounds a bit weird. Then you can also be only happy or sad. And then once you measure, and that's another curious quantum effect, you will collapse this superposition of state to end up in one of the basic states, or either in love, sad, or happy. And here is a little animation to show you how quantum superposition works with photons. And it works like that, like we send a photon on a beam splitter. So we have like 50% probability of it being reflected and 50% probability of being transmitted. In this case, it's we don't have if you run it like an infinite amount of time, you will end up like with equal superposition of both. I'll just run it once again so that you see you have the superposition, and then by doing the measurement, you collapse this superposition of state in either of the two detectors. And then superposition wouldn't be useful by itself, and it would not even be a quantum effect if you wouldn't use interference. So you may have heard of interferences with waves, so either constructive interferences, or like the peak of the waves, they arrive at the same time, and this way it sort of amplify the wave, or destructive interferences, where like the peak of the wave coincides with the lower point of the other wave, and in this case they cancel out and we end up with like nothing. Again, how does it work with photonic? Well, we send a photon on a beam splitter. So we have, after that, it's a 50-50 beam splitter. So we have 50% chance of being transmitted or reflected. And then we apply like a phase shift in order to shift the wave that represented this photon, so that they can either constructively interfere or destructively interfere. And you see that if we keep this phase shift of lambda over 2, all the photon will interfere in these detectors, whereas if we remove this shift of the photon of this path, all the photon will interfere in the other detectors. A crucial property of quantum computation is entanglement. It's maybe the most important one, but it's also the one that is the less understood. So I'll try to give you a nice vulgarized explanation of entanglement. So say you have two persons that can where their states, their mood is like linked to the mood of another person, and it can only be described by this global view. Like if you look at the state of locally at the state of person 2 or person 1, you wouldn't have as much information as if you look at the mood of the two states at the same time. And this can be described like by a quantum state like this. So we are both happy, that's written here, and that's what we find here. Or one is sad, the other one is happy, so that's what we find here. Or both are sad, or one is sad, one is happy again. And we see that this state cannot be is not, so the formal definition of entanglement is really that a state cannot be separable, so it cannot be written as a product of two states, and that's the case with this this example. Again, a little animation to show you how we play like the effect of entanglement with photons. So say we have an entangled state. Here it's represented by photon. So they can be like they can share like same polarization. They can be in the H plus VV state. So both polarized, or both horizontally polarized or vertically polarized. And the outcome of that is that these two detectors will always click at the same time, and these two will always click at the same time. So we observe correlation that is related to the quantum state that we have. And this correlation are quite unique. Like there's certain class of quantum state that enables us to observe correlation that the classical state cannot yield. And this is exactly the topic of non-locality. So again, non-locality is a subtle topic. I'll give you an introduction of it. So we can observe non-locality in the following setup. So say we take two parties, Alice and Bob, that are playing a game. So they've been asked a question, one or two, and they need to answer, give an answer, which is answer one or answer two, but they cannot communicate. And to win the game, the answer must be different to one pair of questions and identical for the others. And it turns out that if Alice and Bob just share like classical resources to play the game, say they share a piece of paper where they predefine the answers they're gonna give to each question, the best score they can get is 75%. Whereas if they share an entangled state, a quantum resource, they can reach a score of up to 85%. And this is a crucial property. It was the such an experiment that will enable Alain Spee and his co-Nobel Prize winners to earn this Nobel Prize last year, to show that indeed, quantum computation cannot be described by a local hidden variable model, we say, and it is just like it proved that just like Albert Einstein was wrong, because Einstein thought that quantum theory was incomplete and it should have been described by a local hidden variable theory. And so they experimented a theorem that John Bell, the Irish physicist, described like in the 1960s. And so now you know what are the main ingredients of a quantum computer. In this next session, we'll study how we have each of these ingredients with a photonic quantum computer. But here I give you an overview of the different type of quantum computer that can play with these properties. So we have either analog devices or digital devices. For analog devices, we have cold atoms that are also known as simulators. They have like between 100 and 1,000 qubits and have limited application. They're like not a universal quantum computer. I must add to this one that QuEra, this spin-off of Harvard recently showed a way to use cold atoms to do digital computing. So now they can be found also in this category. A pretty famous way of doing quantum computation is quantum annealing with a machine like based on superconducting technology like the wave propose. They have up to and even more than 1,000 qubits, but no proven quantum advantage for now. And then on the digital device side, there is the photonic approach, of course, the one that Quandela uses. Then trapped ions used by IonQ or AQT, and then superconducting used by Google, IBM, and Rigetti. But like why all these people like invest a lot of time, of resource in order to build a quantum computer? Well, it's because they're proven algorithm that will bring us on a major quantum computer some speed up compared to the best classical algorithm known. One of them is the Dutch Jozsa algorithm. So it was the first proof of quantum advantage. So a quantum algorithm that solves a problem exponentially faster than a classical algorithm. even though this algorithm was not useful, it was a super nice proof that, well, indeed, we have like computer science argument that there are algorithms that are much better than classical algorithm. Then the famous Shor's algorithm, I'm sure you heard of this one, which gives a quantum advantage for practical application, in theory, of course. And Peter Shor, so as you can see him on the left, he demonstrated that the quantum computer can factorize a very large integers efficiently, and that there is no classical algorithm that can solve this specific problem. So that's the problem definition just below. Also, one must precise that, well, there is no theoretical proof that no classical algorithm exists, but like a lot of really smart people tried throughout the years and nobody found a efficient algorithm for such a problem. And why this algorithm is famous is because it could be used to break the today encryption system called named the RSA public key crypto system, and will enable like a quantum computer hacker to basically break like any data that is encoded today, like bank information, highly encrypted message from government, and so on. Another interesting algorithm is, that yields like a quadratic speedup, which is a speedup that is less important than like the previously presented one by which is exponential with the Shor's algorithm. It's Grover's algorithm for the search of data in a database, an unstructured database using an oracle. And the problem is that we have a data set of n boxes, and we want to that contain binary values. We want to look at the box, increase the cost by 1, and find a box that contains a 1. On a classical machine, we just need like n looks, but on a quantum computer, you just need like square root n queries to solve this problem. Interestingly, and similar to the idea of what Richard Feynman had originally, Seth Lloyd developed in 1986 like a simulation algorithm in order for a quantum computer to simulate quantum mechanical system. He showed that much fewer number and operation were needed in terms of resource consumption, and it has a lot of application in various fields like drug design, high energy physics, material science, and so on. Then then here is a recap of all the main must-know algorithm that we just mentioned, and like the main milestone of the history of quantum computing. So in 1982, Richard Feynman was the first to give this idea of a quantum computer and think of it as a perfect way to simulate quantum mechanical problem. Then David Deutsch gave a formal definition of a quantum computer with like a Turing machine formalism in 1985. In 1992, David Deutsch and Josa, they gave a first quantum algorithm that had a exponential speedup over classical counterparts. In 1994, a first quantum algorithm that proved like gave a practical quantum advantage, still like in theory, of course, with Shor's algorithm. Then in 1996, we had Grover's algorithm for the search in unstructured database, and gave you like a significant speedup for this one. And then in 1996, a quantum algorithm developed by Seth Lloyd about the simulation of quantum mechanics. So here are the key takeaways of this first session. So apart from this historical milestone I just shared about the history of quantum computing, remember that there was a long-lasting battle between the wave-particle duality of light, which the conclusion was brought by Max Planck and Albert Einstein with where they said that light was exchanged in the discretized matter in quantum of light, and that where light was both made of photon and was also a wave, which then lead to the formulation of quantum mechanics. And this was super useful because it enables us to explain that in some experiments, like you can observe some interference pattern with light, and which showed that, well, indeed, light is interesting to build quantum computers. And so as a reminder, we gave like some informal definition of quantum computer, which is important to remember, and the basic quantum properties that we use to do quantum computation. And last but not least, the must-know quantum algorithm and they speed ups. There's a huge ton, there's a zoo of algorithm now. So this is just like the main ones. But let's say that if you really master these ones and the way they work behind, you will understand like easily a big part of the quantum algorithm that there is around here. Thanks a lot for listening. If you have any question, I'd be happy to take those. If not, I will leave the floor to Shane Mansfield, the Chief of Research of Quandela, who will give you an overview of the math behind linear optical quantum computing.
Thanks, Arno. I think Shane has not been connected yet. So
Shane will be connecting in a few minutes, yes.
in a few minutes, right? So do you want to get some questions now, or do you freely from the audiences? 질문 지금 있으신 해주실 분들은 채팅이나 바로 마이크 켜고 해주셔도 되겠고요. 아니면은 4시부터 다음 강사이신 셰인께서 아직 접속을 안 하셔서 셰인님 접속하시면은 그 다음 세션을 4시부터 진행을 할까 합니다.
Maybe what questions are coming in, I can give you a bit more information of what's coming next with Shane about the math behind linear optical quantum computation. Can you see my slide, by the way?
Yes, I can see your slide.
Okay, perfect. So he's going to give you like a description of the basic linear optical elements in terms of matrix, of unitary matrix, and it will show you like how you put several of those and how you compose this operation. Also, we'll talk about like a major photonic quantum computing paradigm, which is boson sampling. So that's a model, quantum computing model that you will hear of often, because it was one that was able to prove the quantum supremacy. And this one can be described by the computation of the permanent of a matrix, which is written just on the bottom left of this slide. So that's for the next session that Shane will give, so the next hour. But tomorrow we continue this presentation with Jean about about how to do quantum computing with photon and give you this broad overview. And we'll talk about Quandela's architecture for quantum computers. So as you can see on the left, that's a scheme of our quantum computer where there are different parts, a source of photon that emits single photons that are then sent on a chip where we process the information, and then we detect those using like single photon detectors and the outcome is measured and sent back to the user who is coding in Perceval. So the framework you will discover in a hands-on session, I believe in week 3 of this training. And we'll also talk about this really general, as we call it, like universal interferometer. So a scheme that can implement any linear optical operation with one given setup, which is crucial for us because, well, we just need one chip and we can do any operation with that. So that's great. And then Nicolas will go in a more practical way. He will describe what's happening under the hood of a photonic quantum computer, especially like how does our single photon source look like. And so you can find here a bunch of pictures and zoom in of our single photon source. And then it will describe also like how our universal interferometer looks like and what's happening in there, like what all these wires and all the fibers coming in and out and so on.
Okay, Arno, I have just received one question
Okay.
from audience. Yes, there are like mainly we know like there are 4 big different ways of creating a quantum computer, and among those, what is like pros and cons of a photonic quantum computer compared to others?
Okay. Thanks, Jasuko, for the question. So there's obviously like now we're in a race of building a full stack a fault-tolerant quantum computer. The photonic approach is quite interesting because first of all, we manipulate photons, which they don't have any mass, no charge, which means that we don't have the problem of decoherence. So I'm not sure you're aware of the notion of decoherence. It's the ability of a system to keep its quantum state for a given time. So with photon, we don't have this issue. Like the system will always keep its quantum state, and not being messed up with the environment. But using photon, we have some loss. We lose photon along the way. So our challenge would be to minimize the loss in our setup. Also, another pro of the photonic approach is that most of what we do is done at room temperature. And what I mean by that is like the information processing. Still, like the emission and detection of photon needs to be cooled down at 4 Kelvin, but that's relatively easy temperature to cool down the system to. It's like technology that it's mastered in MRA, in hospitals and so on. And so this is why we believe it will be easier to scale using our approach. Also, one must talk about the fact that there's only 2 platforms that show the quantum advantage for now. There's the superconducting one. So I'm sure you heard of the Google supremacy experiment, which was then proven to be not as true as they expected, not as big as they expected, but still was the first. But then they further enhanced it and showed that there is indeed quantum supremacy. The second one is the Photonica platform with the experiment of boson sampling that showed the quantum supremacy. So that's a big pro also for the photonic quantum computing approach. Don't know, Jean, if you want to add any point to that.
No, so it's a bit early to say who would be the winner, or maybe there will be multiple winners. You know that there is CPU, there is GPU, there is TPU, there is a lot of different processing units that we can use today, and each of them have their advantage. Shen will tell you a bit about concretely how complicated it is to simulate photonic quantum computer. We are very close to the limit of the simulation of quantum computer today, photonic quantum computer today. That means that beyond 24 photons, will be in an area where we won't be able to simulate anymore the system we are doing. It doesn't mean that we have an advantage, but it means that we are able to do things that we cannot simulate with classical resource. So all of that together, there is no clear answer. What is the best? On our side, we know photonics because it is what we are doing. We believe in photonics. There is another thing that you can remember also for photons. Everybody is saying that they will be connecting quantum computers together. So IBM is saying that. A lot of companies are saying that. And to connect quantum computer, you need photons. So you need photons that will carry the quantum states. And in any case, photons will be part of quantum computer or quantum clusters that we'll see in the coming decades.
Okay, there's one more question from our audience. When the quantum computer become commercialized, do you think it will be overcome the classical computer or will be used for research purpose only? So what do you think about the commercialization level?
Yeah, so maybe the first answer to that is that, well, quantum computers are already being commercialized. So as Jean said in introduction, we delivered a quantum computer to OVH Cloud, so the leader cloud provider in Europe. And for now, like any quantum computer that you will find on the market is you can simulate it with a classical device. You can like, so in other sense, like any classical device would be faster than this one, more powerful than this one. But the idea is that there's a gap, there's a barrier to entry in order to use a quantum computer, and that people need to be trained and start using it, so that once the quantum computer will be faster and more powerful than the classical computer for some use cases, then the company would be ready to use them, and you know, they will be able to leverage and capture the value delivered by the speed of algorithm.
Just to add on Arno answer, there is things that quantum computer will be able to do that nobody will be able to do with classical resource, and it's one of the things that we'll be showing in the next session, not this week, but the following session will go about application of what you can do with a quantum computer. But in short, you need to know that basic things like adding numbers, a quantum computer is very bad of doing that. But very hard things like finding all the permutation of a set of data, photonic quantum computer is very good at doing that. So there is area where a quantum computer will really be able to give some speed up combined with a classical computer. I'm going also on the other question just to keep time. Compared to superconducting or ion trap, how different is in terms of software or control? So personally, I think it's simpler. Photonic, the control is very easy. And it is something that you will be showing tomorrow. You will see the presentation of Nicolas Marin that will show you exactly how is constructed, built a photonic quantum computer, and altogether, so it's relatively easy. Of course, it's hard to find the components, but it's quite easy to build. And the other question that you have, saying how we can manipulate a photon to create a state, it's a very important question, and we'll go through that question tomorrow. There is multiple way with Arno. There is multiple way to create a qubit state with photons, and it is what you call the encoding. So we can use polarization, but we can use also space, we can use time, and this is a very important and critical question when you are using a photonic quantum computer. We have the liberty of the freedom of choosing, which is not the case for other platforms. And this is a very powerful point. So if there is no other question, we will leave the floor to Shane Mansfield that just joined us. Regarding Arno and myself, so we are currently in Denver, which is at the other side of the planet. So we will leave you for the rest of the session because it's very late here. And Shane will go over the mathematics of photonic quantum computer. If there is any question that you have for which we need you need some answer, Shane will be able to cover almost everything. And in any case, we'll meet tomorrow with Arno for the second session. So we are very grateful for you joining this session. And Shane, it's up to you.
All right. Thank you, John and Arno. Thank you very
Thanks
much for your
Thanks a lot
presentation.
for all the questions, and see you tomorrow, everyone.
Yeah, see you. Thank you.
All right. Thanks very much, Jean. Thanks, Arno. Okay, so